So here's the workflow used for the rotor optimization, where the blade loading and stacking parameters are used to generate the blade shape in Turbo Design 1, and then the resulting performance parameters are fed into Turbo Design Optima, which basically applies MOGA to drive the solution towards the optimum design. And of course, we need to specify the range of variation for the input parameters, which are the stream-wise loading parameters and also the trailing edge work coefficient, because it has an influence on the wrap angle and thus the blade stress. And then these are the constraints that are used. So in addition to the throat and the overall diffusion ratio, we constrain some wrap angle related user-defined parameters like the UD wrap, which is the wrap angle difference between the 15% span and hub at the blade trailing edge. The UD-RMSE calculates the root mean square error of all the wrap angle difference between these various locations, which would be 0 for a perfectly radial fibered blade. And so this is limited as well. And then this UD work is calculated by the volume flow averaged RV theta variation between the leading and trailing edges, and is related to the turbine power through Euler turbomachinery equation, and needs to be constrained also. And finally, for the optimization objectives, we want to minimize the profile loss and also the leaving kinetic energy in order to maximize the efficiency. But at the same time, we also want to minimize some more wrap angle UDPs, like the UD max deviation, which is the maximum value of all the wrap angle differences used in the calculation of UD-RMSE before. And lastly, we want to minimize this UD maximum bow, which is the maximum deviation from linear span at 90% of the streamwise location near the trailing edge, and would be 0 for a perfectly radial filament blade. So in this way, using these wrap angle UDPs, we ensure that the blade integrity is not compromised in the process of improving its aerodynamic performance. And in fact, this methodology was successfully used in one of ADT's recent technical papers that was presented at the 15th IMECI Turbocharging Conference. So once the optimization run is complete, which is very fast and only takes about an hour or so on a single core machine, we can see all the designs on a scatter plot between any two objectives. In this case, the maximum bow on the x-axis and the maximum deviation on the y-axis. And here we have chosen to see only the feasible designs, which respect all of our specified constraints, and the target case, which is the baseline 3D rotor, actually sits here. And then we can choose to see the Pareto front of optimum designs, from which we can pick and analyze any case of interest. And in this case, we select a design which gives us the lowest combination of the maximum bow and maximum deviation, and thus brings us as close as possible to a radial filament design. And so we use this design for further analysis and for comparison with the baseline rotor. And in fact, this is what changed as a result of the optimization. So for the streamwise blade loading, the optimizer increases the aft loading at the shroud even further in order to reduce the profile loss. And for the span-wise work distribution, you can see that the optimizer recommends leaving a slight swirl at the trailing edge for improving the blade wrap in this area. And as a result, the optimized rotor is clearly looking very different from the baseline rotor. So while the baseline 3D rotor had a high lean or wrap at the trailing edge, the optimized design features a much more radial blade, which should help reduce the stresses in this area. And so first, let's have a look at the mechanical performance of the optimized rotor. And so as far as Turbo Design 1 performance parameters are concerned, there is a substantial improvement in various wrap angle related UDPs, due to which the wrap angle distribution in the optimized rotor is actually quite close to radial filament near the extruser region. And as we can see here, the FEA analysis proves final confirmation that the peak stress in the optimized rotor is contained well within the yield strength of the material. Now, although there is a small region of high stress on the pressure side trailing edge, but this is mainly caused by the lack of modeling the fillet. And finally, what remains to be verified is the aerodynamic performance of the optimized rotor, and it's interesting to see the effect on the turbo design 1 parameters, where there is a significant reduction in the total profile loss and the exit kinetic energy as a result of the optimization. And when we run stage CFD analysis with the optimized rotor at 3 different rotational speeds, we find that the peak stage efficiency actually stays quite close to the baseline 3D rotor and is noticeably higher compared to the radial filament rotor. And in fact, the benefits are even more at the off-design speeds and reach up to 3 points improvement at the higher speed. And of course, the mass flow rate continues to remain aligned with the design value of 0.31 kg per second, and the close match between the rotor work coefficients and TD1 and CFD is still maintained.